Okay, so we're on the last unit, confidence intervals for the slope of a population regression line. So there's something called a population regression line. Notice we're using Greek letters here, A or alpha plus beta x, where mu of y is the mean value for a given value of x. Alpha is the population y-intercept. That makes sense. Mx must be there. And then b is the population slope. So again, using those letters, we're talking about the population regression line. But there's also a sample regression line. If you take a sample and do a regression line with that data, then those we use a plus bx instead of alpha and beta there. Notice they're referring to the slope of the y-intercept. They're not type 1, type 2 errors. That's a different use of alpha and beta. So I know that's a little confusing, but we're not talking about errors in this case. Okay, so this is interesting. So the mean of the sampling distribution of B is mu of B equals beta. So beta is the mean. So it's kind of weird. When you're talking about regression lines, the mean is the slope. So it's like a mean slope. It's beta. If the 10% condition is met, we can use a formula for standard deviation. Formula is a little different here. So it's got a little different twist that we haven't seen before. It's a special formula. It's on your formula sheet for that. And it uses, just to mention that, it uses the standard deviation of the residuals, sigma x, is the population standard deviation of the explanatory variable x. So we have sigma divided by sigma x, and then also divided by square root of n. For the population of 263 Old Faithful eruptions in a particular month, the population regression line is that. The standard deviation of the residuals is that, and the standard deviation of the eruption duration, sigma x, is that. Okay, so they give you all the stuff you probably need here. Imagine taking a simple random sample of 15 eruptions that occurred during the month and using the sample data to calculate B, the slope of the sample regression line for predicting y wait time until the next eruption. Calculate and interpret the mean of the sampling distribution of B. So remember, mu of B is beta. So beta is 13.3. Okay. This is going to be a little hard to understand, but it's just basically kind of parroting back the question there a little bit if you look at it here. So if you selected all possible samples of 15 Old Faithful eruptions during this particular month, calculate the slope of the least squares regression line. All that's now the context of the problem. If you read it, it's what they're saying that you're doing this problem. The sample slopes would have an average value of 13.3 is what we're saying here. If you selected all possible samples of size 15. So that would be a true sampling distribution. If you have that, then the sample slopes, the average of the sample slopes would be the population slope, which is 13.3. Verify the 10% condition is met. $15 is less than 10% of all 263 eruptions in this particular month, so that's good. 15 is less than 26. If we plug into the formula all the stuff we know there, we get a standard deviation for B of 1.42. Again, similar idea here. If you selected all possible samples of size 15, so a sampling distribution and calculate the slope of the least squares regression line. For the context of the problem, the slopes would typically vary from the population slope of 13.3 by about 1.42. Okay, now these are the conditions, and that's, I would say, a big part of today's lesson here. We're trying to learn how to do these four conditions, A5, linear. So we want the data to be linear. We're to show how to check that. It should make sense with what we've done in the first semester of the course. We want to make sure it's normal. Distribution y and x are normal. It needs to be equal standard deviation. Random sample, or randomized experiment, and then less than 10% conditions. So really, there's 5 conditions there. So I like this description here. So how do you check and see if the data is linear, the regression line is linear? So look at the scatter plot. Does it look roughly linear? Okay. Also look at the residual plot if you have it, and say there shouldn't be any curve patterns. The residual plot should be somewhat scattered. That would indicate it. So that's an example of a good scatter plot. So the first part of that check, look at the scatter plot. Does it look somewhat linear? I'd say it does. If the residual plot look like that, you're in a world of trouble, right? Because it's a curve pattern. You don't want to see a curve pattern. You want to see scatter. Okay. Normal. Well, how do you check this? It's not as easy as you might think. Make a dot plot, stem plot, or box plot, any of those guys, for the residuals. So you're making a box plot of the residuals. Now, sometimes they just do this for you, right? So, in fact, oftentimes, you don't want strong skewness or outliers. So oftentimes we don't have enough points, so that's why we have to use the residuals here. If the graph shows no strong skewness or outliers, we're good. So it's reasonably accurate, even when the distribution has strong skewness, if the sample size is large. Okay, so equal standard deviation. This one's kind of weird. We're not used to this one. We haven't done stuff like this, really. Look at the scatter plot. Above and below the line y residual equals 0 line. Variability of the residuals in the vertical direction should be roughly the same from the smallest to largest value. So vertically, it should be roughly the same. Common violations include a pattern. The residuals tend to grow in size as x increases, or the residuals tend to shrink in size. So I don't like the vertical pattern there. They tend to have a pattern there, so that's bad. Random, that should say it in the problem, less than 10%. If it's done without replacement, which is anything other than experiment, needs to be less than 10%. Okay, so let's look at an example. Maybe this will make more sense. The U.S. Forest Service randomly selects ponderosa pine trees in western Montana to investigate the relationship between diameter breast height, and volume of usable lumber. Scatter plot shows relationship between X and Y there for a random sample of 40 ponderosa pines. And they, again, fortunately give us all this information. We have to use these 3 graphs to check all the different conditions. Right, so let's try this. They say, you can almost call this liner, L1NER, as an acronym. So L stands for linear. So you look at the scatter plot first. Looks pretty linear. That's good. Look at the residual plot next. Looks pretty scattered. That's good. I'd say it passes the linear condition. Normal, you want to look at the histogram of the residuals. Doesn't look somewhat symmetric. No outliers. We're good. In the residual plot, we do not see a clear vertical pattern there. So I think it looks somewhat evenly spaced there. It looks fine. Random sample of 40 ponderosa pines in western Montana. So it says that in the question, actually. And 40 is less than 10% of all the ponderosa pines in western Montana. That's true. Don't sweat the small stuff on when checking the graphs for normal and equal standard deviations. Should be fine, usually. So, again, tropical cyclones, known as typhoons or hurricanes, are intense circular storms that originate over warm tropical oceans. The low air pressure associated with these storms can cause very damaging winds. For the population of 193 tropical cyclones over an 11-year period, population regression line is that. The standard deviation is that, so forth. Okay. Calculate, interpret the mean. So look at the population regression line, find the slope, negative 1.24. So negative 1.24 is your mean of the sampling distribution of B. If you selected all possible samples of 16 tropical cyclones, there's a full sampling distribution during this 11-year time, and calculate the least squares regression line for predicting that stuff in context, the sample slopes would have an average value of negative 1.24. So because 16, you had a sample size of 16 is less than 193 tropical cyclones, we can then check we can actually plug into the formula there for standard deviation, find the standard deviation, and then interpreting that be if you selected all possible samples of size 16 tropical cyclones during this 11-year period in the context of the problem. The sample slopes would typically vary from the population slope of negative 1.24 by about 0.084. Like this question, so we're trying to check the conditions here. When they give us the three graphs, very common for them to do that. So linear doesn't pass the linear test. The scatter plot looks linear, and the residual plot is somewhat scattered, so we're good. Normal. So the histogram of the residuals looks approximately symmetric, no major outliers. That looks good. Equal standard deviation. If you look at the residuals, that second plot there in the top right, vertically it looks fine. It doesn't look too patterned there. Oh, we see a pattern. We see a less than pattern. Oh, I see what it's saying. Okay, so do you see how the points are more bunched up on the left and not as much on the right? So we see a less than pattern that doesn't pass the equal standard deviation. Oh, that's a good example of that one. I really like that example actually. So that is not met. So it's not talking vertically. It's saying it's kind of looking at the horizontal spacing. To me, they said vertical in the last one, but I really think almost that like horizontally you want it somewhat equally spread out there, and it's more bunched up on the left. That's not good for equal standard deviation. It is random, and it is less than 10%, but it needs to pass all the conditions, and it doesn't. So that's your lesson for today.